Welcome to the video for Lecture 7, Section 3. In this video, we will cover two theorems that will provide us ways to find some useful information about dynamic process described by differential equations that have been transformed into the Laplace domain. They are the final value theorem and the initial value theorem. The first theorem is the final value theorem. We will use this theorem to find the steady-state behavior of our dynamic time-dependent process. If the expression includes the process, sensor, feedback, controller, and actuator elements, we can look at the overall long-term response and we can determine if the response is stable, oscillating like a sinusoidal wave, or will blow up. To be able to use the final value theorem, both the time-dependent function and the first derivative must be Laplace transformable. If those conditions are met and the limit of ft exists as t approaches infinity, then we can find the limit of ft by multiplying the Laplace domain function fs by s and taking the limit as s approaches 0. We will find that final value theorem applies whenever the time function and the first derivative are Laplace transformable, and the roots of the Laplace transform are either 0 or negative real roots. If any of the Laplace transform roots are positive, the final value theorem does not apply. Let's go through a couple of examples and see if the final value theorem applies and what is the time domain function final value. These examples are the same ones in Section 7 of the course packet. For example 1, we are given the Laplace domain function, so we will assume that the time domain function and the first derivative were Laplace transformable. The first step is to find the Laplace domain expression roots. The methods were discussed and demonstrated in Section 6 of the course packet. For the Laplace domain expression fs equals 1 over s times s plus 1, the roots are 0 and minus 1. Since the roots are 0 and negative real roots, the limit as t approaches infinity exists. The second step to find the final value using the final value theorem is to multiply the Laplace domain function by s. The expression becomes s over s times s plus 1. This can be simplified as 1 over s plus 1. When we take the limit as s approaches 0, the expression approaches 1 over 1. So using the final value theorem, we find that time domain expressions as time approaches infinity is going to be 1. We can confirm this by taking the inverse of the Laplace domain expression on the previous slide, 1 over s times s plus 1. The easiest way to take the inverse is to recognize that we can use equation 19 in the Laplace transform table to invert the expression. The time domain expression for ft is 1 minus e to the power minus t. As t approaches infinity, the second term approaches 0, so the time domain expression approaches 1, just as we found using the final value theorem. For simple problems like this, we demonstrate that the final value theorem works by solving the equation and seeing what happens as t approaches infinity. Here is another example where we are given a Laplace domain expression. Again, we assume that the original expression and the first derivative are Laplace transformable. Then we start by finding the roots of the Laplace domain expression. We found the roots for this expression in Section 6 of the course packet. They are 0, minus 1, and minus 1. Since other roots are 0 or negative real values, the limit exists. To find the final value using the final value theorem, we multiply the Laplace domain expression by s. When we multiply the Laplace domain expression by s and simplify it, the expression becomes 1 over s cubed plus 3 times s squared plus 3 times s plus 1. When we take the limit as s approaches 0, the expression approaches 1 over 1. We can confirm this again by taking the inverse of the Laplace domain expression given the roots and using the partial fraction expansion. This was done in Section 6 of the course packet. The time domain expression is ft equals 1 minus e to the power minus t times t squared over t minus t minus 1. As t approaches infinity, the e to the minus t term approaches 0, so the time domain expression approaches 1. Here is a third example, where we are given the Laplace domain expression shown here. As we have done before, we find the roots. With this complex polynomial expression, we will need to use MATLAB to find the roots for the denominator. The expression is written in three forms. The top is the original. The middle expression is written with the denominator in the pole form. In this form, the roots are obvious. They are 0, 2, minus 1, minus 2, and 1. The third form is written as a single polynomial. This is the form that we can use to write the MATLAB roots expression. We can use MATLAB to find the roots by using the roots expression for a polynomial with coefficients of 1, 0, minus 5, 0, 4, and 0. Note the 0 terms that were included to communicate to MATLAB that there are no s to the 4th power, s squared, or s to the 0 power terms. MATLAB returns the results that the roots are 0, minus 2, minus 1, 2, and 1. These are the same roots that we had on the previous slide. Now getting back to using the final value theorem, we need to look at if we have positive roots. If yes, then we cannot use. And in this case, we have two positive roots, 2 and 1, so we cannot use it. So to find the final value using the final value theorem, we multiply the polynomial by s. When we do so, we get the expression shown here. Again, we can find the inverse expression using MATLAB to find the partial fraction expansion and then take the inverse. The time domain expression xt is given here. Notice that we have two terms that do not go to 0 as t approaches infinity. The e to the power 2t and the e to the power t terms don't go to 0 as t approaches infinity, so we cannot apply the final value theorem to the expression. So this proves that if we have positive roots, we cannot use this theorem. For this class, you will stop working on final value theorem problems once you find a positive root. You will simply report that the function has a positive root, so the final value theorem does not apply. Sometimes it is useful to know the initial value of a function just after time 0. Remember that in dynamic process analysis, an input function will change at time 0, so we want to find ft just after it. You may see this written as the value of f at t equals 0 plus. Similar to the final value theorem, the time domain function and the first derivative need to be Laplace transformable. And the limits of s times fs needs to exist as s approaches 0. Then the time domain value of f at time 0 plus equals the limit of s times fs as s approaches infinity. Here is an example. Let's find x at 0 plus time given the polynomial expression shown here. The first step is to multiply the expression by s. Then we expand the denominator to get s to the 4th power minus 5 times s squared plus 4. At this point, it is important to recognize that the expression in the lower right corner of the slide has equal power in the numerator and the denominator. Both the numerator and the denominator have s to the 4th power terms. We need to use long division to reduce the power of the numerator. The next step is to apply long division to the polynomials. So the expression can be written as 1 minus s squared minus 9s plus 12 over s to the 4th minus 5 times s squared plus 4. To apply the initial value theorem, we need to see what the function does as s approaches infinity. In this case, the denominator gets larger faster than the numerators because the denominator has s to the 4th power while the numerator has an s squared term. This means that as s approaches infinity, the limit approaches 1. The initial value of x just after t equals 0 is 1. This brings us to the end of this video on the final value theorem and initial value theorem. Please write down any questions you have and bring them up in class.